Good morning, everyone. So, in our previous week, we learned about the soil seepage and we calculated the in situ state of stresses for the three cases: no seepage, upward and downward seepage. So, this is the continuation of the seepage chapter. So, in today's lecture, we will talk about the two numerical examples to calculate the total stress, pore water pressure, and effective stress. Then we can apply the knowledge of the seepage, for example, the limiting or the critical hydraulic gradient to calculate the safe cut excavation in clays. So we will also solve one numerical example on that. Then similar to the seepage stresses, we will simply multiply it with the area to convert it to the seepage forces and then divide it by the volume to know about what is the seepage force per unit volume. Then we will talk about Professor Tarzaghi concept of heaving in soil due to the flow around structures such as sheet piles, dams, excavations, and we will try to solve one of the numerical example around the sheet pile. Then there is an extremely important phenomena to control these built up of seepage stresses in the earth dams and to avoid the failure against the piping or the seepage. We provide the filter at the toe of the dam, and so we really need to know what is the design criteria. So we will talk about that also. So this is the numerical example. So in this numeric example, you have to note down if this is suppose point A. So point A to B, there is a groundwater table. There is no soil, and the height of the groundwater table is 6 meter. From point B to C, there is a saturated sand, and it has the unit weight of 19.25 kilonewton per meter cube. And the thickness of the soil deposit is 13 meter. And you are asked to draw the stress profiles, and one is the total stress, second is the pore water pressure, and the third one, if you know total stress and pore water pressure, you can calculate the effective stress. So other than Mehran and Fahad, anyone would like to tell me the values or how we are going to calculate? I would be very happy to know about that. No one knows how to calculate the stress, total stress.
Sir, A से B तक sir total stress
Okay, I can't hear you. Okay, so you have to learn how to speak in front of the microphone.
Sir, A से B तक हमारे पास जो होगा sir ये H
No, no, no. There is something wrong with your microphone. Please make sure.
Sir, can I?
No.
Sir, मैं
Yes,
बताऊं?
please.
Can I speak, sir?
सर सबसे पहले हम लोग क्या नाम है हाइट को मल्टीप्लाई करेंगे विद gamma W मतलब के वाटर यूनिट वेट ऑफ वाटर फ्रॉम A to B. जैसे 6 मीटर इंटू gamma वाटर आपने जो यूज करना है.
Okay, that's
9.
fine. Okay, then
Yes sir.
at
Then
point
again
C.
हम लोग yes sir हम लोग 13 को मल्टीप्लाई करेंगे विद 9.81 to get from B to C.
And we will also add this stress from A to B. So at point B, you have only this much overburden. On point B, this much is the stress. So that's 6 times unit weight of the water. And at point C, you have this stress plus you have the stress due to this saturated sand. So it means 6 multiplied by 9.81 plus 13 multiplied by 19.25. So this is the total stress profile for the for this problem. So let us calculate the pore water pressure. So pore water pressure at point A will be 0. Pore water pressure at point B will be 6 multiplied by 9.81 and pore water pressure at C, because the voids of this sand are filled with water, so that will be 13 multiplied by uh, 13 multiplied by 9.81 plus 6, and also this you have to add in this what we call is the, because at over this point you have this much pore water pressure and this much pore water pressure. Then you are going, you know, if you know the total stress, if you know the pore water pressure, then you just simply need to deduct the pore water pressure from the total stress to calculate the effective stress. So these values will cancel each other, and then 309 minus 186, you will get 123 kPa. I really suggest all of you to plot this on a graph. I may give such problem in quiz or in exam. Okay. So, and then if I ask you to draw all the profile on a single graph, so you can see that this is the uh, total stress, this is the pore water pressure, and this is the effective stress. So I simply plotted with different legends. So this is solid line, this is dotted green line, this is another dotted line, black line. So this is how you plot the stress profiles of any problem. Now let us solve another problem so that it will be more clear to you. Now in this problem, you do not have water at this point. It is a dry sand from A to B. Okay. So it means at A there will be 0. At B you will be having 16.5 multiplied by 6, the total
Excuse me,
stress.
sir.
Yes.
सर ये 290 का माइक ऑन है, तो आप प्लीज जरा इसे म्यूट कर दें क्योंकि बहुत ज़्यादा डिस्टॉर्शन हो रही है आपकी आवाज़ में.
Sorry.
सर ये 290 का माइक ऑन है, तो उसको ज़रा आप म्यूट कर दें क्योंकि आपकी आवाज़ नहीं आ रही ठीक.
Okay. So who is 29? क्या रोल नंबर है? 29.
सर 290.
I will make him, let me remove him from class. Maybe he is sleeping, I don't know. Okay. Is it clear now?
Yes sir, yes sir.
Okay, so at point B, you have a stress due to this overburden of the sand, and that you will calculate 16.5 times 6 will be the total stress at point B. Then at point C, you have saturated sand. So at point you have a dry sand from A to B, then plus the saturated sand B to C is 13.13 multiplied by 19.25. So you will add, so the total stress at point C will be 16.5 multiplied by 6 plus 19.25 multiplied by 13. This is the total stress. Now let us calculate the pore water pressure. So pore water pressure at point A will be 0. Pore water pressure at point B will also be 0 because the groundwater table is located here. But the pore water pressure at point C will be 13 multiplied by 9.81. Okay, because the pores are the voids of the sands are filled with water, and to calculate the effective stress you are simply going to deduct. So this will be the profile of the effective stress. Now you can plot all of these values on a single plot to show the stress distribution. Any question how I calculated, because this was already taught you in my previous lecture. So if you understand the previous lecture, definitely you can understand these numericals. Okay, all right. So I assume every one of you understand this. So now let us apply
Yes,
the knowledge of the seepage on one of the practical problem of the, if, okay, now suppose you have a condition where there is a clay, okay, there is a clay, and below clay you have a very permeable ground. You have a highly permeable ground, the ground which has a very high permeability value. So that can be sand, it can be
or
gravel.
gravel.
Okay, so this is the condition you have to, if, okay, now if this is the condition and you are proposing कि you wanted to have basement, you want to construct a basement या आप कोई excavation करना चाहते हैं, तो you don't know कि यहाँ पे आप कितना कट करें, कितनी डीप excavation करें कि कोई failure ना हो. So you wanted to know the maximum safe cut height. So what maximum safe excavation against the heave failure or against the sand boiling? So what is the condition of the sand boiling? Sand boiling की क्या condition है? Sand boiling
इफेक्टिव
की
स्ट्रेस जीरो हो
condition
जाता
है,
है
sorry, yes,
सर इफेक्टिव स्ट्रेस जीरो हो जाता है सर वहाँ पे
very good. So sand boiling condition is case effective stress should become zero. And why this effective stress becomes zero? Because we already have proven that if there is a upward seepage, there are two hydraulic gradient, one is I critical and one is I, okay, so I will show you I average. Okay, this is something I will drive equation today. So if your hydraulic gradient is greater than, average hydraulic gradient is greater than I critical, then your factor of safety become less than 1. I will teach you this condition, and this is why we have a heave failure in such conditions. Anyways, but every one of you agree from previous lecture that effective stress becomes zero because of the increase in seepage, hydraulic gradient increases, and that make effective stress zero. Now effective stress zero mean like at point A you have to calculate the effective stress. So it means at point A you need to calculate the seepage, sorry, you need to calculate the total stress and pore water pressure. So total stress minus pore water pressure will be the effective stress. And it also says that the unit weight of the clay is 120 pounds per feet cube and unit weight of the sand is 108 pound per feet cube, but we are not going to use this unit weight. Okay, and it says that at point A the water, if you install a piezometer, the pressure head is 12 feet, so from which you can calculate the pore water pressure, and in clay there is no pore water pressure. Okay, now let us calculate the total stress at A. So who would, so now let's assume that this is the H cut height that we can excavate. So this is assumption. It means at point A, this is the overburden stress. So this will be 20 minus H would be the height, 20 minus capital H. Okay, now 20 minus capital H will be the total stress multiplied by the saturated unit weight of the clay. This will be the, what we call is the total stress. Now if you install piezometer at A, then you have a groundwater table of 12 feet, means the water head is 12 feet. The pressure under Artesian condition. Okay, so it means that you have to calculate the pore water pressure as, or the water head as 12 multiplied by 9.81. So this is the pore water pressure. Now if you want to calculate the effective stress at A, then simply sigma subscript A minus pore water pressure subscript A will be your effective stress, and that has to be zero for the heave failure or for the quicksand condition. Okay, so you can see sigma A minus UA, which is the effective stress, Okay, then you have to put equal to 0, and simply by rearranging this equation you can calculate the capital H. So again, if there would not be any gravel or sand at this location, we don't need to perform these calculations. Any question related to this problem?
सर ये 20 किस तरह है?
Sorry,
ये सर ये 20 किस तरह है?
क्या किस तरह है?
20 माइनस 8 इसका समझ नहीं।
20 किस तरह है?
यस सर।
Okay, so at point A आप ये तो एक्सकेवेट कर दोगे, और हमने अज्यूम किया है कि जो सेव एक्सकेवेशन की हाइट है वो कैपिटल H है, जो हमने कैलकुलेट करनी है। तो A के ऊपर कितनी सॉइल रह गई है, जो थिकनेस है वो कितनी रह गई है? हेलो, हाउ मच इज द थिकनेस ऑफ सॉइल अबव पॉइंट A?
बस ठीक है सर, 20 माइनस 8 समझ आ गया सर, उसका हाइट 20 है और उसका
ओके, गुड, ऑलराइट. Okay, so let us see another problem. So in this problem, it says this is the same problem which I solved in my previous slide. So they performed a borehole, they drilled a borehole, and borehole says in 25 feet there is a clay, and below 25 feet there is a gravel or sand, and you know gravel or the sand has a very high permeability, and the groundwater table is in sand or gravel. So when they drill the borehole and leave the borehole, after steady state condition, they measured the level of the water in this borehole, and that is 18 feet. So it means that the piezometer or the water head in the sand is 18 feet. Now they want to have the open excavation. For example, they want to have this much excavation here. Okay, capital H, such that they do not have any failure. So again, you need to basically calculate the stresses, total effective stress at this point, and you have to put equal to 0 for the heave condition, and this will be 25 minus H. Okay, this is similar problem to the previous, and the total stress at A will be 25 minus H multiplied by 113.4, and pore water pressure at A will be 18 multiplied by 9.81. So by rearranging this equation, you can calculate the what we call is the safe height of the excavation without any failure. So you can do it. If there is any issue, you can get back to me. Now let's see. This lecture we talked about no seepage condition, we talked about upward seepage condition, and we talked about downward seepage condition. So this was the seepage force, and so this is the total, this is the effective stress in upward seepage, and if you multiply it with A, this will become the effective stress to effective force. Now this was the seepage force, this was the seepage stress, and upward seepage we assume positive, and if you multiply with A, this will become the seepage force. So the seepage force in upward condition is seepage stress multiplied by area, and if you divide it by the volume, so the volume is, suppose this is the cube that we are considering of soil, it have the area A and the depth Z, so the volume will become AZ. Now you can see that Z will be cancelled, A will be cancelled. So the seepage force per unit volume will be I, which is the hydraulic gradient time unit weight of the water. So please remember that we always talk about the seepage force per unit volume. We do not say seepage force per unit area. So whenever I will be solving the heave problem, I will be talking about the value of the seepage force per unit volume. And you know how I got this value I, Z, gamma, W, this is from previous lecture. So Mehran, can you tell us what is meant by the seepage force per unit volume?
सर इसमें सीपेज फोर्स पर यूनिट वॉल्यूम में सर हम सीपेज ये फोर्स ले लेंगे सर। मतलब पहले इससे पहले जो हमारे पास इफेक्टिव स्ट्रेस के साथ जो टर्म या ऐड हो रहा था अप डाउनवर्ड कंडीशन में और अपवर्ड कंडीशन में वो माइनस हो रहा था, वो हमारा सीपेज प्रेशर था सर। उसके साथ हमने एरिया मल्टीप्लाई किया तो वो सीपेज फोर्स बन गया। उसके बाद हमने
Okay.
सर फोर्स पर यूनिट वॉल्यूम फाइंड करने के लिए उस सॉइल का वॉल्यूम फाइंड कर रहा है जो Z इंटू ए, तो बाद में वो I इंटू गामा W बन जाता है सर
All right.
सीपेज।
Okay, I got it. Thank you. Now, so it means that if I give this in exam or MCQ or somewhere, okay, what is the seepage force per unit volume? So you should never forget that it is hydraulic time the unit weight of the water. Now let us understand what is heaving in soil around these structures. So we are talking about sheet piles, dams, or excavations. Okay. So the seepage force per unit volume, which I told you in my previous slide, which is equal to I hydraulic gradient time unit weight of the water. So the seepage force per unit volume of the soil can be used for checking the possible failure of the sheet pile. So you know what is sheet pile, okay? Now structure where underground seepage may occur, there is a possibility of the heaving on the downstream side. So what does that mean? Let me show you. So you know who is he? He is basically Professor Tarzaghi, and he developed this understanding of very important phenomena in soil mechanics, which is applied to global structure of billion of dollars, okay, around the globe. So you can see he is, I think, sitting in the MIT soil mechanics lab, and he provided us this particular configuration. So you can see there is a sheet pile, there is a retaining structure, and on the upstream side there is the freeboard height of the water, which is H1, and there is a permeable strata through which there can be seepage. Okay, so you know flow nets, you know equipotential lines, okay, and the thickness is T, and on the downstream side the pressure head or the head of the water is H2. Now he says he investigated lot of experiment, and he says that if this is the embedded depth of the sheet pile in the permeable strata, this is the embedded depth of the sheet pile or dam or what we is the excavation, then d by 2 width, on the d by 2 width there is always a failure. So he says this is the area where there always is the piping or the heaving failure. So the soil fails, and because of this failure this sheet pile has a collapse. So this is, now if I zoom in this failure wedge, then this capital D is the embedment depth of the structure in the permeable stress strata. This U is the uplift seepage force, and you know how to calculate it because the uplift below dam we calculated using the flow nets graphical solution of the seepage. Okay, and how we got this d by 2 as a width, this is the empirical width which Professor Tarzaghi has reported, and we use this in analysis. And capital W is basically the weight of the wedge that is going to be failed. So Fahad, can you revise this slide please? Fahad is not in lecture. So Zain Tariq, quickly please.
सॉरी सर, वो मेरा
Okay Fahad, you have to
इंटरनेट
speak
आज
loudly please.
ठीक नहीं है सर, वो मेरा इंटरनेट ठीक नहीं है, बार बार डिस्कनेक्ट हो रहा है, आज तो डिफिकल्ट हो रहा है सर।
Okay, so Zain. Okay, Mehran, can you revise this slide? What Professor Tazari has told us about the heaving and what is heaving?
ये सर इसमें सर प्रोफेसर तरदागी ने एक्सपेरिमेंट किया सर, शीट फाइल के अराउंड एक एम्बेडमेंट लगा दी जिसकी डेप्थ थी डी और विड्थ थी d/2। तो उन्होंने इसमें सीपेज फोर्स पर यूनिट वॉल्यूम को यूज करते हुए ये फेलियर शीट फाइल की फाइंड करना चाहिए।
और ये d/2 ने कैसे पता चला? ये d/2 क्या है?
सर d/2 पे जो है ये इसकी फेलियर होती है सर एम्बेडमेंट की।
Okay, and this has been proven by experiments. All right. So let us see now. So Professor Tazagi in 1922 conducted a lot of tests, and I told you in the previous slide that based on those tests, he said that failure always or the heaving generally occur within the distance of d/2 from the sheet pile. And what is capital D? I told you is the embedment depth of the structure, okay, into the permeable layer. Sorry. Okay. So thus now when we analyze all of these structure, जब ये हम डैम्स बनाते हैं या शीट पाइल बनाते हैं या जो basements जहाँ पे पानी हो या ये सबवे stations, तो we have to analyze the stability against the heaving. So ये वो wedge है जिसकी heaving की stability. So हमें पता होता है कि what is the embedment depth of our structure in the permeable layer. So if we know this, we can know d/2. तो इसकी width calculate करने में तो कोई issue नहीं है. Weight, if we know d/2, if we know the unit weight, we can calculate weight by multiplying the density by the volume. Okay, you can calculate because density is equal to weight by volume, and you know how to calculate the density of the soil. And who would like to tell me how to calculate this U and what is U? No one knows. Okay, and how to calculate that practically?
वो सर पोर वाटर प्रेशर के फाइंड करेंगे, फिर उस पे सिम्पसन रूल लगाएंगे, ग्राफ लगाएंगे।
No, this is not accurate. Anyone else?
तो ये सीपेज की वजह से जो अपलिफ्ट फोर्स होगा।
Okay, Mehran told this is uplift force due to the seepage, but how to calculate that? What do we need?
Flow nets, sir.
Nets.
Yes, very good. So you should say flow nets, okay? Anyways, now factor of safety against heaving can be given by, so see there are simply Fy, there is a equilibrium. So if your weight of the soil is higher than this uplift, there will be no failure. So it means factor of safety is W/U. Now let's see what is W. Is the submerged weight of the soil and U is the seepage uplift force. Now how to calculate W? It is very simple. This is the volume, because out of plane you will take 1 meter. So D is the depth, d/2 is the width, and 1 meter. So this is the volume. And then you will multiply it with the gamma submerged, means the submerged density of the soil. So this is the volume multiplied by density. This is the weight. And you know submerged unit weight is equal to gamma saturated minus gamma W. So if you rearrange this equation, this will become 1/2 d square gamma submerged. So I already told you U is the uplift force. So we are going to solve one practical example. Okay. Now how to calculate U? U is equal to soil volume multiplied by seepage force. Sorry, seepage stress. So if you multiply it by seepage stress, because this is the seepage force per unit volume multiplied by the soil volume, this will be total seepage force. And you know K 1/2 is the d square is the volume of this wedge, multiplied by I average is the hydraulic gradient, and as Fahad has told us that we need to draw the flow nets. Then using the flow nets, we can calculate the average hydraulic gradient. So if we know average hydraulic gradient, unit weight of the water is known, capital D is the embedment depth, so you can calculate the factor of safety. Now if your factor of safety is greater than 1, what does that mean? Physically उसके क्या meaning है? अगर आपका फैक्टर ऑफ सेफ्टी ग्रेटर देन 1 है इस इक्वेशन में, तो क्या इसका मतलब है कि W डैश योर वेट ऑफ द वेज इज हायर देन द सीपेज stresses, so it means कि there will be no failure, and if it is equal to 1, it means कि it is on the verge of the failure, and if your factor of safety is less than 1, it means it will definitely fail. Any question related to this slide? What is meant by the factor of safety? So Fahad, can you revise this slide please?
सर
Zanta,
प्रोफेसर दागी ने जो एक्सपेरिमेंट्स किए उससे हमें ये पता। Am I audible, sir?
I don't know why you don't speak loudly. Do you have some problem with your microphone?
सर मुझे नहीं पता इसका।
Yes, you should learn how to talk in front of the
अभी
microphone.
सही है सर।
Okay, now it is clear. So can you please revise it?
सर प्रोफेसर जागी ने सर जो एक्सपेरिमेंट्स किए थे उसमें ये कंक्लूड हुआ कि जो जनरली जो सर हमारे पास हीविंग की फेलियर्स होती है वो d/2 ऑफ द फाइल शीट में होती है, जो एम्बैंकमेंट की जो d/2 है उसमें होती है। तो जो स्टेबिलिटी जोन हमारे पास डेवलप होता है सर वो d मल्टीप्लाई बाय 2 d/2 का जो सेक्शन है d हमारे पास जो आउट ऑफ प्लेन हम उसे 1 मीटर कंसिडर यूजुअली 1 कंसिडर करते हैं, यूनिट कंसिडर करते हैं, और d/2 उसका सर हमारे पास ये दूसरा सेक्शन क्रॉस सेक्शन का दूसरा लेंथ हो गया सर। तो उसके लिए हमें फिर फैक्टर ऑफ सेफ्टी डेवलप करनी पड़ती है ताकि हम उसे इस तरह से डिज़ाइन कर सके ताकि हीविंग ना हो, जो कि हमारे पास बराबर होती है फोर्स मल्टीप्लाई बाय फैक्टर ऑफ सेफ्टी एस वो सबमर्ज वेट डिवाइड बाय सीपेज फोर्स बराबर होती है।
Okay,
सर तो
thank you.
सबमर्ज
So
वेट
Mehran,
हम
all right, thank you Fahad. मेहरान, इसमें कौन से वेरिएबल हैं अगर मैं कहूँ कि जो हमें कैलकुलेट करने हैं?
किस चीज में सर?
फैक्टर ऑफ सेफ्टी की जो इक्वेशन है उसमें कौन से वेरिएबल्स हैं जो हम कैसे कैलकुलेट करेंगे? यूनिट वेट के कोई इशू नहीं है, और बताओ आप।
आई एवरेज सर।
So the challenging is I average. So we will learn how to calculate I average in our next slides. Okay, so simply this is the factor of safety equation. So if I summarize this will be cancelled, d square will be cancelled. So there will be only gamma dash divided by gamma w divided by I average. Now who would like to tell me what is gamma dash by gamma w?
I critical, sir.
I critical, sir.
Very good. So it means that factor of safety will become the function of the hydraulic gradient, and that is I critical divided by I average. So you can understand how we derive the equation of the factor of safety for the sheet pile. Now let us solve one of the practical example. Okay, before solving practical example, let me show you some conditions. So this is a sheet pile, and this is a permeable strata, this is impermeable strata. So it means that there is a H1, H2. Due to the difference of energy or the head, there will be the downward seepage. Because of this seepage, there will be uplift pressure, and you have to look on the wedge, and d/2 has been has been reported by the Professor Tazagi. This capital D is, we already know how much is the embedment depth. So this is the configuration that I already have explained in my previous slide. Now let us see dam example. So this is an example of the dam. So you can see this is the concrete dam, and this is the permeable strata, and this is impermeable strata. There will be the seepage. Now this is the downstream side. So on downstream side there is a sheet pile, and why we have this sheet pile? Because it is typical to prolong or to increase the path of the seepage. Okay, so to increase this path of the seepage. Anyways, now this sheet pile has some embedment depth D, and there is there is likely to have a seepage failure of the wedge, and this is D by 2, this is capital D. This is one of the example. Okay, you don't need to get confused कि sir D की depth ये है तो ये मतलब this is just a representation. So this is always D, this wedge is always D depth, and this is D by 2, and this is an excavation. So maybe basement or subway station, or what we call is the underpass construction, and this is the initial groundwater table. So they first install the retaining structure like diaphragm walls, and then because this is you can see this is also permeable, this is also permeable, there is a groundwater table, definitely there will be a seepage. So if this is the embedment depth capital D, okay, then you have to check the stability of this wedge. So these are just an example that it's not like you can only what I can say is you have to only check the stability of sheet pile. You can apply this concept to any geotechnical problem where there is possibility of the upward seepage and permeable strata. So let us see, this is the practical example in which you have been given a sheet pile. Okay, so this is the sheet pile, this is the upstream. Okay, so let me. Okay, so this is the upstream side, and the pressure, this you are given the head difference as 7 meter. So this is 7 meter. Okay, and you are given this embedment depth as how much is 10 meter. Okay, and you are also given the flow nets. So the flow nets are given to you, so you know how much this would be. This would be 5 meter, means D by 2, and you are given the unit weight or the saturated unit weight of the sandy soil or the permeable strata, and that is 19 kilonewton per meter cube. Now your task is to evaluate the factor of safety or the safety of this wedge or this entire structure against the heave analysis using Professor Terzaghi method. So you know कि factor of safety against heaving is equal to gamma I critical, okay, divided by I average. Now I average we have to calculate using the flow net. I will explain in next slide, and how I can calculate the I critical कौन बताएगा?
I critical is equal to I submerged over I sorry gamma submerged over gamma W.
Okay, very good. So gamma submerged क्या होगा कौन बताएगा? 19 minus 9.81, okay, divided by 9.81. So it means the only thing which I need to calculate is I average, hydraulic gradient average, and where I have to calculate hydraulic gradient average from which location, let me show you. Okay, before going, you can see how many equipotential drops are there. 1, 2, 3, I think 10. Okay, so n subscript d are 10. So you know the flow nets. Okay, and I already told you in my previous lecture what are the flow nets, what are the equipotential drops. So these are the things that you need to review if you do not understand from my previous lectures. Anyway, so let us solve this. If I zoom in this portion, so we can drive this. So you can see that this is 5 number equipotential line. This is 6, 7, 8, 9, 10. Okay, and how I got this D and D by 2, this was told by Professor Terzaghi to look into stability of this wedge only. So I'm not looking into flow net and equipotential drop at this location or this location or this location. I have to look into only B, C, E, D wedge. which has dimension of small d and d by 2. Now I average we have to calculate, and you know hydraulic gradient is basically dH divided by d. So the head loss divided by the distance over which the head loss happens. So head loss is from BD, so from this depth to this depth. So we have to look the hydraulic gradient in this range to calculate this head loss and divide it by d. So small d you already know, but you do not know what is the head loss from here to here on this wedge. So let us see how to calculate that. So the head loss in this wedge is equal to delta H total head loss divided by total number of equipotential drop multiplied by number of average equipotential drop from BD to CE, from this location to this location. Okay. Now capital delta H, how much is delta H? This is already given to us, the total head loss, which is 7 meter. How much are the n subscript d? Who would like to tell me? You can calculate equipotential drop 1, 2, 3, so on 10. So this is given to you. Now only thing we need to calculate is the average number of the equipotential drop. So if I know average number of the equipotential drop, I can simply calculate. So let's see number of equipotential drop from B to C, from here to here. So these are how much? 1, so 1, 2, 3, 4, and 5. So there are 5. Now let us calculate the equipotential drop on this face DE. So then I will take the average of CE face and DE, and that will be n subscript number of equipotential drop average between C for this entire wedge. So 5 are on this face, and so this is 1, 2, 3. Okay, so from D to E is almost, we can say, this is 1 equipotential drop, this is 2, and this is 3. Okay, you can have 3 equipotential drop instead of 2.7. Okay, so this is a graphical solution. I already told you. Okay, I can explain you how these are 2.7. So this is one equipotential drop. Please look, this is one equipotential drop. This is 2 equipotential drop. The third equipotential drop lies between this and this, and this is not complete. So you have to look on only into this. So this is approximately 0.7. Is it clear?
Yes, sir.
Yes, sir.
Okay, again. Please see, this is one equipotential drop. This is another equipotential drop. The third equipotential drop is this much, but our wedge ends over here. So if this is, you can take it 0.6, 0.7, 0.8 as an approximate. Okay, so that's why we have 2.7. So on face BC you have 9 equipotential drop, and on face ED you have 2.7. Now average will be 5 plus 2.7 divided by 2. This is 3.85. So it means the head loss from BD to CE means this location to this location, from the bottom of the wedge to the top of the wedge. You have this value, you have this value, and you also have this value. You only need to insert the values, then you get the head loss. Now if you put this head loss in this equation and you divide it by the distance over which the head loss happens, and small d is given to us, is how much is that? Small d is 10 meter. So you can calculate I average. Now you see I average is 0.27, and I critical gradient we already calculate gamma dash by gamma w. So let us take the ratio, and the factor of safety is 3.48. So is it safe or it will fail? Who would like to tell me?
सेफ है सर, सेफ है
Save
सर.
as the hydraulic gradient is greater than 1. Now, when you will design, you will not design for 1.5. You always design for 3 or 4 as a factor of safety. So, as a geotechnical design engineer, when you will be working on a design problem, so for the safer side, you have to design for 4 to 5 factor of safety, not for 1. Okay, because there can be many uncertainty during construction, during seepage flows. So we always design with the conservative design. Any question how I solve this practical example? Mehran, is it clear?
Yes sir.
Okay, good. So let us see, uh, let us conclude about this heave that the factor of safety against heave is recommended 4.5 in design practice. Okay, this is about the design practice. So inherent accuracies in analysis, that's why to increase factor of safety against the heave, quicksand, boiling, piping. So whatever I taught you, the anyone can use word piping, boiling, quicksand, heaving. So these are same words. Now, how to solve this problem? We have to design filter on the downstream side. What does that mean? We will look into that. But what are the filters? Are the highly permeable materials such as the sand or the gravel. And why we want to have that? Because if we have a highly permeable material at the end, so the seepage forces will dissipate and there will not be, we do not allow to develop the seepage pressure or the pore water pressure. Now there are few conditions. So the condition one by the Professor Tarzaghi for the filter is that you should have small openings. Small openings should be present in the filter. For example, if this is a very large gravel, to have a very permeable high permeability, then you need to have also the small particle inside, so that जब सीपेज होगा तो जो वाटर के पार्टिकल हैं दे विल ट्राई टू वॉश आउट द डैम और द स्ट्रक्चर सॉइल पार्टिकल. सो यू डू नॉट वांट to have the washout of the base material. So you want to prevent the base material. For that you need to have the small enough openings. I will explain it detail in next slide. The second condition is you should have a highly permeable material as a seepage material, because you do not want to allow for the seepage forces or the hydrostatic pressure. So simply whenever some material, some water or the seepage, the water due to the seepage is collected in the filter material, it should be drained out. So let us see what is meant by that. Now you can see this is a sheet pile, this is the upstream side, this is the permeable strata, this is unpermeable strata. So due to the seepage, the water pressure will happen over that, and Professor Tarzaghi told us that this is D by 2, okay, and this is D. Now, so what we will do, we will design this some depth of gravel mixed with some sand, some material over here, and this is known as a filter material, and this prevent basically the heaving failure which we discussed in our previous slide. Okay, so it means y d by 2, y d, what is w dash, I already told you what is u. Okay, now an additional layer of the filter material is added which has d1, and this is the weight of the filter. Okay, now you already know कि फॉर एग्जांपल ये सीपेज स्ट्रेस तो वही रहेगी या सीपेज फोर्स पर यूनिट वॉल्यूम. हम अब जो ये डब्ल्यू डैश है, जो ये वाली टर्म है, ये अगर हम इंक्रीज करेंगे तो फैक्टर ऑफ सेफ्टी ग्रेटर देन 1 आएगा. ओके, सो टू इंक्रीज इट वी आर इंट्रोड्यूसिंग वन न्यू टर्म, and to calculate the weight of the filter material, which is equal to again the volume is 1 out of plane multiplied by this d by 2 multiplied by this d1, okay, multiplied by unit weight of the or the density of the filter material. And density of the filter material you can calculate by the any dry density or the density lab experiment. So if we solve this equation, this will become this one. Now in this equation, this is the unit weight of the filter material, no issue, we can calculate that. This is submerged unit weight of the soil, we can calculate that. I average, how to calculate, I already explained you in our previous lecture, okay, in our previous slide. Gamma W is the constant, capital D is the embedment depth of the. Now first you will have, for example, you say let's have 1 feet of the filter material and you calculate and your factor of safety value is 2. It is still safe against the heave, but I told you design recommend 4 or 5. Now you will increase this capital D, let's make this 3 feet, and suppose your value of factor of safety comes 4, it means you have designed the filter depth D1 accurately. So is it clear how to design this capital D1? So you will calculate factor of safety until you get the design value. You will write in your drawing of design that this is the depth of the filter. Now filter material कौन सा होना चाहिए वो हम next slide के ऊपर बात करेंगे. So Mehran, can you explain how to what is filter material, why we are adding filter material to increase this to make the factor of safety greater than 1, और फिर ये D1 हम कैसे कैलकुलेट करते हैं हिट एंड ट्रायल से, और हम क्यों 4 and 5 वैल्यू रखना चाहते हैं? कैन यू आंसर ऑल ऑफ दीज क्वेश्चन?
सर इसमें सर फिल्टर मटेरियल इसलिए यूज़ करते हैं क्योंकि तरजागी ने जो कहा कि ये शीट पाइल से इधर जो डिस्टेंस D/2 पे जो ये फेलियर आकर होते हैं, तो इन्होंने एक सॉल्यूशन रिकमेंड किया कि बेस मटेरियल के ऊपर हम फिल्टर मटेरियल.
ओके, आई कांट हियर यू, प्लीज, यू डोंट नो हाउ टू टॉक इन फ्रंट ऑफ द माइक्रोफोन.
सर इसमें
यस, ओके, कंटिन्यू.
सर इसमें ये फिल्टर मटेरियल इसलिए यूज़ किया था ताकि ये जो फैक्टर ऑफ सेफ्टी है उसको बढ़ाए. अब तरदागी ने सर कहा था कि शीट पाइल के इधर जो D/2 डिस्टेंस होता है उस पे D/2 डिस्टेंस पे ज़्यादा फेलियर अगर होते, तो इन्होंने बेस मटेरियल के ऊपर फिल्टर मटेरियल रखा ताकि उस फेलियर को हम कम कर सकें या उसको बिल्कुल ख़त्म कर सकें. तो इन्होंने D/2 पे फिल्टर मटेरियल रखा सर. और यहाँ फैक्टर ऑफ सेफ्टी कैलकुलेट करने के लिए इससे पहले तो हमारे पास सबमर्ज वेट ऑफ ये बेस मटेरियल था. अब इसमें सबमर्ज वेट ऑफ फिल्टर मटेरियल भी आ गया. उससे हमने फार्मूला लिखा है, उसमें सर एक मिनट आ गया D1. अब इसमें सर डिज़ाइन में जो रिकमेंडेड होता है वो 4 to 5 होता है, तो हम हिट एंड ट्रायल करेंगे, D की वैल्यूज पुट करेंगे ताकि हमारे पास जो रिक्वायर्ड फैक्टर ऑफ सेफ्टी है 4 to 5 आ जाए.
डेप्थ ऑफ द फिल्टर.
यस सर, D1.
और इस तरह हम डिजाइन करेंगे. ओके, थैंक यू मेहरान. ऑलराइट, नाउ अभी हमें ये नहीं पता कि अब ये फॉर एग्जांपल कि ये मटेरियल कौन सा हमने यूज करना है. सो लेट अस सेलेक्ट द टाइप ऑफ मटेरियल ऑफ दिस फिल्टर. सो डेप्थ वी डिजाइंड. ओके, नो द सिलेक्शन ऑफ द फिल्टर मटेरियल इज यूजुअली ग्रैनुलर मटेरियल. और क्यों ग्रैनुलर मटेरियल कौन बताएगा? मैं पिछली स्लाइड्स पे बता चुका हूँ. व्हाट इज द रीजन टू हैव द ग्रैनुलर मटेरियल?
कि तरदागी ने कहा था कि उसमें स्मॉल ओपनिंग्स होनी चाहिए.
नहीं, ओपनिंग साइज की तो बात ही नहीं है. एनीवन एल्स अबाउट द ग्रैनुलर मटेरियल?
हाई परमेबिलिटी.
इससे सीपेज होगा तो स्ट्रेसेस बिल्ड नहीं होगा सर.
Very good, because it's a highly permeable, its K value is very high, so whenever water will come, it will dissipate and there will be, it will release the stresses. So this is why we wanted to have that. So the condition 1, I already told you that there should not be very large opening, कि वो जो मटेरियल सीपेज के जो पार्टिकल हैं वाटर के वो अपने साथ फाइन पार्टिकल ऑफ द क्ले लेके तो वो वॉश आउट ना कर दें और वहाँ पे पाइपिंग फेलियर ना हो. सो दिस इज कंडीशन 1. Condition 2 is something which someone answered, that we need to have the highly permeable material, okay, so that there is no built up of the pressure. Now this is the answer. This is Tarzaghi and Peck, and Professor Peck is also very famous. He has worked with the Professor Tarzaghi, so they came up with the design equations in 1948. Now to satisfy the condition 1, so this is your material दैट इज प्रेजेंट एट योर साइट, जो शीट पाइल के अराउंड है, जहाँ से सीपेज हो रहा है, या जो डैम जिसका बना है, ओके, जिसके डैम की बॉडी बनी है। सो दिस इज नोन एज द बेस मटेरियल। सो यू नो D85 उसकी तो हमारे पास PSD कर्व ऑलरेडी होगी, ओके। सो दैट इज सपोज दिस PSD कर्व, ओके, ये वाली PSD कर्व आपके पास है जिसका आपने डैम बनाया है, या जो अराउंड द शीट पाइल है, या जो अराउंड द एक्सकेवेशन है। Now you will multiply this with 4 to 5 to calculate D15 of the filter। तो ये दो कर्व्स आप, फॉर एग्जांपल ये कर्व A और B कैसे बनी है? So you will develop this curve C, okay, and curve B. How you will develop it? So let me show you. Now this is your condition 1। ओके, सो कंडीशन 1 में आप क्या करोगे कि इसको 5 टाइम मल्टीप्लाई करो ना इसके साथ, तो यू विल गेट दिस पॉइंट, ओके। देन फॉर कंडीशन 2 यू हैव टू मल्टीप्लाई D15, आपकी जो भी मटेरियल है, ये कर्व तो आपको ऑलरेडी पता है जिसका आप डैम बना रहे हैं, जो बॉडी बना रहे हैं, उसका आपने D15 कैलकुलेट किया। यू ऑलरेडी नो हाउ टू कैलकुलेट D15। सो द इफेक्टिव साइड D15 ये आपके पास आया। यू विल ड्रॉ अ हॉरिजॉन्टल लाइन, ओके, एंड ये हॉरिजॉन्टल लाइन आपने ड्रा कर दी यहाँ तक, ओके। दिस इज हाउ यू विल ड्रा हॉरिजॉन्टल लाइन। देन कंडीशन 2 की इक्वेशन आपको गिवन है, यू विल कैलकुलेट D15 ऑफ फिल्टर, तो उसके बाद आप 4 या 5 से मल्टीप्लाई करेंगे तो आपके पास वैल्यू आ जाएगी। वो वैल्यू आपकी सपोज आ गई कोई भी वैल्यू, ओके। सो यू विल ड्रा अ लाइन अप टू हियर, okay, and then you will develop these equation by drawing this point and this point. Similarly you can draw curve C। so to cut it short, अब आपके पास जब ये कर्व B और C आ जाएगी इन कंडीशन से, तो आपके पास एक रेंज आ जाएगी। तो आपने अपना जो फिल्टर है, उस कोई भी मटेरियल उसकी जो PSD कर्व है वो लाई करनी चाहिए इस रेंज के अंदर। सो दिस इज हाउ द पार्टिकल साइज डिस्ट्रीब्यूशन कर्व, जो कि एक बड़ी सिंपल कॉन्सेप्ट है हाइड्रोमीटर एनालिसिस और सीव एनालिसिस का। यू कैन इमेजिन कि उसकी बेसिस के ऊपर ये बड़े बड़े डैम डिजाइन हुए हैं अगेंस्ट द फेलियर। नाउ देयर आर मोर कंडीशंस which has been written in the BM Das book. For example, the filter material should not have the grain size greater than 76.2 millimeter 3 inch, okay, to avoid the segregation. So in concrete you may have read the meaning of segregation। ये होते हैं कि फॉर एग्जांपल जो हैवियर पार्टिकल हैं वो साइड पे हो जाएं और डिफरेंट हो जाएं, और जो लाइटर पार्टिकल हैं, सो वी वांट टू हैव द मिक्स ऑफ द लार्ज पार्टिकल एंड द स्मॉल पार्टिकल। दैट इज द आइडियल केस, एंड द सेग्रीगेशन इज के लार्ज पार्टिकल अलग हो जाएं और स्मॉल अलग हो जाएं। तो इसलिए जो भी आपकी फिल्टर मटेरियल की PSD कर्व है उसके अंदर इस साइज के पार्टिकल नहीं होने चाहिए। दिस इज कंडीशन 3, यू कैन चेक दैट। कंडीशन 4, टू अवॉइड द इंटर मूवमेंट ऑफ द फाइन इन फिल्टर। इसका मतलब ये है कि जब सीपेज होगा तो उसके साथ अगर फाइन पार्टिकल ऑफ क्ले आ जाएं तो यू शुड नॉट अलाउ। तो इसलिए जो आपका फिल्टर मटेरियल है, इट शुड हैव 5% पासिंग फ्रॉम द नंबर 200C। 5% से ज़्यादा नहीं होनी चाहिए फाइन्स की, वरना वो फाइन्स जो है उसके अंदर क्लॉग हो जाएगा फिल्टर, तो वो जो एम्प्टी स्पेसेस हैं वो फाइन से भर जाएंगी। फाइन्स की बड़ी लो परमेबिलिटी होती है और वहाँ पे बिल्ट होगा सीपेज प्रेशर। Condition 5 is when perforated pipes are used for the collecting seepage, filter are also used around the pipes to protect the fine-grained soils from the being washed. To avoid the movement of the filter into the drain pipe, the following conditions should be satisfied. Okay, for example, if there is a road और रोड के नीचे हमने कोई पाइप दिया है ड्रेनेज को कलेक्ट करने के लिए, तो इस पाइप के अंदर अगर ये पाइप है सपोज, इसके अंदर स्मॉल होल्स होंगे, इस पाइप को हम कहते हैं परफोरेटेड पाइप। तो उसकी परफोरेशन के अराउंड आपको एक जो फिल्टर आप देंगे फॉर एग्जांपल, तो उसकी मूवमेंट को अवॉइड करने के लिए भी कंडीशंस हैं कि जो भी आप फिल्टर डिज़ाइन करें उसके जो पार्टिकल्स हैं वो ग्रेटर देन होने चाहिए जो ये साइज होगा। फॉर एग्जांपल इट हैज़ सपोज 3 mm के जो है ना ये होल्स हैं इस पाइप के अंदर जो आप यूज़ कर रहे हैं ड्रेनेज के लिए, तो 3 mm मल्टीप्लाइड बाय 1.25 आप करेंगे तो आपके पास एक वैल्यू आ जाएगी। तो जो आपका फिल्टर मटेरियल के 85% सॉरी D85 जो आपका फिल्टर मटेरियल 85% पासिंग का जो आपका साइज है वो उससे ग्रेटर होना चाहिए। जो स्लॉट विड्थ है, अगर वो विड्थ है या अगर वो डाया है, अगर वो इस तरह है, ठीक है। सो इट डिपेंड्स ऑन दैट। ओके, एनी क्वेश्चन रिलेटेड टू हाउ टू सेलेक्ट द मटेरियल फॉर द सीपेज? ट्राई टू लुक इनटू दीज स्लाइड्स और फिर एक कर्व ले लो, खुद ही अज्यूम कर लो और उससे कैलकुलेशंस करने की कोशिश करो। बट आई थिंक दिस इज प्रीटी मच clear to you because every one of you understand what is the filter, what is the seepage, what is the granular material, what is the permeability, low, high, sand, gravel, clays, fine particle washout. You also have idea about the PSD curve. You know what is the effective size diameter, D10, D85, D55, D65. So these everythings are known to you. These are one of few examples. For example, you can see this is the phoretic line, which I already told you. You can calculate using the Schaffer-Knox solution. You can calculate using the Duppert solution. Okay, there are many ways. Now this is the toe filter of some granular material in dam which has been constructed. This is one of the examples. So this is another example in which this is the toe filter. Okay, in this example this is known as the chimney type filter. So you can see if how the water can be collected and it can wash out over here and there will be no seepage stresses. Now these design are not part of this subject. The design of the dam is there is a one of the uh, optional elective subject in your 7 and 8 semester about the dam engineering. So if you want to know how to design these filters in dam, you have to take that elective. Okay, here we are just learning what are filter, how to design the depth of the filter using the soil mechanics heave analysis concept, where we have the factor of safety, and how to select the material for the seepage. And we have a limited scope, so for details you have to learn in dam design engineering, which is your 7th or 8th semester elective. So those who are interested, they can take that elective. This is just to show you one of the seepage failure due to the piping. So you can see that this is the shell material of the Tanton Dam, which, okay, this is the drain, this is the chimney drain that I have shown you in my previous example. ये highly permeable granular material का बना हुआ है. This is the core, and on this side there was a water. So you can see that because of a small seepage, यहाँ पे सीपेज हुआ, फेल हो गया, डेफिनेटली उनका जो फैक्टर ऑफ सेफ्टी होगा वो लो होगा. देयर कैन बी मैनी रीजन एंड हाउ लार्ज इज द फेलियर, एंड यू कैन लुक इनटू द फेलियर बाय लिटरेचर रिव्यू. सो इफ आई समराइज द इंटायर लेक्चर, we use the sieve heaving concept to calculate the safe excavation in the clays, and the condition is that there should be the highly permeable strata below clays, then there can be a heaving failure. Then we use the Professor Tarzaghi concept to calculate the factor of safety against the heaving. Then we learn why we need to have the filter, because we want to prevent the heaving or the piping or the sand boiling failure. And we learn how to calculate the factor of safety if we have the filter, and then by hit and trial we calculated D1, the depth of the filter, to meet the design requirement. Then we learned the PSD curve and how to select the material for the filter. Now this was all about the lecture, and there is a small assignment and you have to learn it by your own self, and in Das book it is also given, so you can learn from that. In your intermediate level, in your FSC or AO levels, you have learned how to how the water rise in the tube by the capillary water action, and the concept is the surface tension. Now using this fundamental concept, you have to demonstrate that how we can correlate this with the capillary rise in soil. and there is a Hazen 1930 approximate height of the capillary rise and typical value of the capillary rise for sand and clay. So you have to learn and you have to summarize and you have to submit assignment. You can look into Google, you can look into YouTube, you can look into Das book to understand it. Any question related to entire lecture? No question? Okay, so I think we are done with today's lecture, right? Mehran, okay?
Yes, sir.
Okay, so have a good day and try to cover up everything. Okay, now after this chapter we are left with two chapters. One is the edit stress, and we will finish that in next week, and last 2 weeks we will spend upon the consolidation chapter. So okay, have a good day.